So just before we begin, I did send around an email announcement through the Moodle forum, but I have started putting up the solutions to the exercises from my notes as we go through the course. So just near the top there, solutions to my exercises. So there's a PDF file there. At the moment, it's just got all the solutions to the ones from chapter 1. As we go through, I'll update them as we go through, okay? But I encourage you to attempt and work on all these questions first without the solutions. So I don't put them up straight away because you're trying to, learn how to solve these things and work through these things yourself. So, but I do put them up, a week or two after the questions have been issued, so to speak, or we've covered them in lectures, to just as a useful tool for you to go back and work with. And I have been handing out from time to time some extra handout sheets. So there was one on extra sequence problems, and there's now also a solution file to that. So you can open that up. And there's the problems that were on that together with full work solutions. And also the handout on proving the quotient form of the algebra of limits theorem. I've now added to that handout kind of the solutions. You can see the solutions in blue there to each of the steps. And then it ends with a final, putting it all together, it ends with the final proof of the quotient form of the algebra of limits theorem for sequences. Okay. So if you haven't looked at that, I'd encourage you to go back and have a good read through and study of that. So that brings us to today's lecture. Last time, just a brief recap on what happened last time. Last time we introduced the notion of series and convergence of series. And we looked at two examples of series. These examples were examples 2.2 and 2.3. So I'll just briefly remind you of those. And that will lead us in then to the topics we're going to consider today. Okay. But first of all, I'll just remind you of what the definition of convergence for a series was. I think it's important to know what we're dealing with. So a series, and a series looks like this. It's the sum of n equals 1 to infinity of some elements xn. So you've got an x1, an x2, an x3, and so on. You're adding them all up, and you never stop the process. You just keep adding them up. So this is x1 plus x2 plus x3, etc. Now this is said to converge. So just repeating the definition of convergence that's in the notes. It's said to converge if and only if. So the thing that follows the phrase if and only if is the definition of this word converge, or the criteria for convergence that must be satisfied. It's said to converge if and only if the sequence of partial sums now this is a sequence sk, where k equals 1 to infinity, and how are they defined? Well, sk is the sum of the first k terms of the sequence. So not the infinite sum, but a finite initial sum, taking in the first k terms. So x1 plus x2, all the way up, but finishing with xk. The series, the original series itself does not finish. It's an unending process of adding up terms. But each of these partial sums is just a regular old boring finite sum, just adding up a finite collection of numbers. But you add up more and more each time. So let's finish the sentence. It's said to converge if and only if the sequence of partial sums is a convergent series. Convergent sequence, sorry. In the sense of chapter 1. So sk must tend to some limit L as k tends to infinity. That's what it means for the series to converge. The series converges if its associated sequence of partial sums is a convergent sequence. In this case, we write So this is how we arrange things. So we can actually say that an infinite sum, an infinite series here, has a definite value. Okay, if you're thinking of it as some kind of mechanical process, adding things up, and each step takes a certain amount of time. Okay, this is an unending process. It's an infinite process. However, given our understanding of sequences, lists of numbers, and how they can converge, if the associated sequence of partial sums is a convergent sequence, then we say that the original series converges and that L is its value. So it has a sum. And if this does not hold, of course, we say the series is divergent. Okay. Now, I don't want to fall into the trap of completely re-giving last time's lecture, but I'll just very briefly bring the two key examples from last time to mind, because they do follow on to what we're going to look at next. So two key examples. So the first one was a convergent one. Obviously, you can write down an infinite series where you're adding loads and loads of big things together. Of course, if you add loads and loads of big things together, an infinite number of them is clearly going to be divergent. The sum is going to just get larger and larger. It's not going to converge to anything. The interesting cases happen when the things you're adding up are extremely small and they're getting smaller and smaller, because then at least there's a chance that the infinite sum might converge. There's a chance it won't continue to get larger and larger. So this is one such sequence here. You're taking 1 over 2 to the power m. And m is going from, well, let's actually make it go, m is going from 1 to infinity. So this is a half plus a quarter plus 1/8 and so on. Adding up the reciprocals of the powers of 2. And, well, if you just draw a number line and track what's happening to the partial sums, you see that this is converging to 1. We'll fit that into a more formal proof type framework when we come to look at geometric series, because this is an example of a geometric series. But if we don't know about that yet, you can just analyze what happens to this on the number line between 0 and 1. First you step to a half, then you add on a quarter, so that brings you up here to 3/4, and you add on an eighth, brings you up here. So you keep on stepping halfway towards 1. So you never step past 1, and you get arbitrarily close to 1. Okay, so this converges to 1. This converges, and we say that the sum of these things from m equals 1 to infinity is 1. Is that okay? Any queries about that example that we looked at last time? Any clarification I could give to it? Further clarification? Okay. So that's nice. There's an infinite series that converges. Now, one way of describing the reason it converges is the bits you're adding on are getting smaller and smaller. See, the extra little steps forward you take are themselves, the steps are converging to 0. Okay? So that's what means that this series, although it never ends, you keep on making it bigger, but you never actually get past 1. Okay? So you only ever add on half of the remaining distance to 1. So that's an explanation of why this, or part of the reason why this converges. The step size is converging to 0. But the second key example was called a harmonic series. And this is a very important example because this is a divergent one. And it shows you that just having a step size that converges to 0 is not enough. See, this one initially looks kind of like the powers of a half that we just looked at. So you're adding up an infinite number of things, and the things you're adding are getting smaller and smaller, and they're converging to 0. Okay, because the fraction 1 over m then gets larger. This is converging to 0. It's 1 plus a half plus a third plus a quarter. So, however, we gave the argument last time. I'm not going to repeat it here, but it involves grouping these terms together. We gave the argument last time, so the grouping argument from last time showed that this diverged. Grouping argument from the last lecture shows that this diverges. And then we played around with some Jenga blocks and then stacked some Jenga blocks, and we showed that if you try to stack Jenga blocks to get them to produce an overhang, you can watch this in the video of last week's lecture, that when you analyze one kind of semi-optimum way of stacking Jenga blocks, when you analyze it, you see the emergence of the harmonic series in the formula for the overhang. And that forced us to the kind of semi-paradoxical conclusion that when you're stacking blocks on top of each other, in principle, hypothetically, you can produce any amount of overhang that you want, even though you're just resting these blocks on top of one another. There's no glue or anything. Each block is just supporting the one above it. But nevertheless, you can, in theory, produce any arbitrarily large overhang. Okay. So, that's good. I think the signature sheet is, did it make it all the way down the middle? Yeah. So I think that's okay. Any last few people can sign it at the end. So it's very important to consider what these two examples are suggesting. The first convergent one kind of illustrates that if you're to have any chance of converging at all, it must be that your step size, the terms you're adding on, are getting smaller and smaller. That's what it suggests, or it illustrates. However, the second example illustrates that that is not enough. Just because you have step sizes that are getting smaller and smaller, you can still be divergent. Okay, that's what this example shows. So that leads us on to, if you glance at the notes there, beginning on page 14, we have got kind of 2 or 3 pages of convergence tests. So the next lecture and next week, we're going to be working through these convergence tests. Now, what are these? These are tests which, for any given series, so if somebody puts a series down on a page with the terms defined by a certain formula, these convergence tests are, if you like, a collection of tools or a collection of arms or weapons or something that you can try applying to any given series, and they may or may not, the tools may or may not say that the given series converges, or they may say that it diverges. Okay, so they give various conclusions. Let's just run through the names. There's a general term test that can detect divergence. We'll talk about that in detail shortly. It's a geometric series test. The geometric series test is unusual in that it gives a complete description of its subject. So it applies to geometric series that have this form here, where each term is a fixed multiple of the previous one. So the geometric series test is unusual in that it completely describes the situation. It says which geometric series are convergent, which are divergent, and for the convergent ones, it tells you what the value is, what the value of the infinite sum is. There's a simple formula here for it, a over 1 minus r. So we'll consider that in detail, probably not today, but probably tomorrow. Then there's an integral test, which again can detect convergence and divergence by comparison with integrals. It doesn't ever tell you what the actual value of the infinite sum of the series is. We've got 2 kinds of comparison tests. But what the comparison tests do is if you already have a series that you know the convergence or divergence of, if you already have a known series, a series that you know that it converges or you know that it diverges, you can use that as a comparison to the series in question. And if the series in question that you're looking at, if it compares in a certain way, which the tests describe, if the series has a certain relation to the one you know about, then you might be able to conclude that the series in question also converges, or perhaps it also diverges. Okay. So you compare a given series to one with known behavior, and then it allows you to draw conclusions about the behavior of the series in question. So for any given series, maybe you can compare it to a known series using the comparison tests. Then there's further tests. Alternating series tests. This applies to terms of alternating positive and negative, to series which have alternating positive and negative terms. And finally, there's a nice one, the ratio test, which allows you to detect, the ratio test allows you to detect series that are nearly geometric, or that are approximately geometric series, and therefore allows you to draw similar conclusions about their convergence or divergence. Again, it'll never tell you what the actual value of the infinite series is, but it will sometimes allow you to draw conclusions about the convergence or the divergence of the given series. And then there's yet more, the root test. It's a kind of unusual one, but involves taking nth roots of your series term. So, I mean, I just quickly zip through the names of them, quickly zip through some brief explanations of them. We're going to go through them slowly in detail, but these are like a collection of tools that you can use to try and answer the question for a particular series. Does this series converge or does it diverge? And maybe sometimes it tells you what the actual value of it is in the case of geometric series. So that's the general kind of problem that we attempt to answer in this chapter. For a given particular series, we can examine the series and maybe we'll be able to say it converges, maybe we'll be able to say it diverges. Okay. First of all, though, we're going to have a look at theorem 2.2. So before we get on to comparison tests, we'll quickly, because it's relatively easy to do, we'll do this linearity result. Now you'll recall for sequences we have this big theorem, the algebra of limits theorem for sequences, that allowed us to take the known convergence of two sequences and then look at sequences that we build out of those two known sequences. We built new sequences in three ways. First way was taking linear combinations of the original two sequences. Second way was taking products of the two sequences. And then the third way was taking quotients, taking a fraction, one sequence term divided by another. So now that we're looking at series, and we've defined convergence of series in terms of convergence of sequences, maybe we'd expect a similar result for series. Okay. So the kind of leading question into this is there a similar result for series that is like, let's look up the number of it, theorem 1.2. Theorem 1.4. This was the algebra of limits for sequences. Well, okay, the answer for us now is going to be kind of. It's kind of a similar result. Not in the case of products and quotients, but yes, in the case of taking linear combinations. So here's theorem 2.2. And we go to the proof because it's possible to give a nice, fairly quick proof of it. So let's look at the statement. If you look at the statement of it in your notes, theorem 2.2 on page 13, it says, suppose we have two convergent series. So we got two series in our hands, but we know that they converge. We've got a series AN, A1 plus A2 plus A3, and a series BN, B1 plus B2 plus B3. Okay. And we know, we'll suppose that we know that they converge. The first one converges to a limit A, capital A there you see, and the second one converges to a limit capital B. Now we suppose that we create a new third series. And the new third series, you can see, is defined by taking a linear combination of the corresponding terms of our original two series. Okay. So the new series looks like the sum of alpha am plus beta bm. So using the assumptions in the theorem, we form a new series let's give it a new name. So it's the sum of elements Cm, where the Cm, each Cm is defined as alpha times Am plus beta times beta. So this is a linear combination of the original two series that we did. And what we want to show is that this new series is itself also convergent. And it converges to, you can see there right at the bottom of page 13, it converges to the obvious sum. If someone sat you down and said, listen, I'm going to force an answer out of you. If you've got an A series converging to capital A, a B series converging to capital B, you form a linear combination of the two series, alpha times the first one plus beta times the second one. What's the new limit going to be? There's only one obvious answer. We mightn't be sure, we mightn't be that confident about the answer, we might want to prove that it is the case, but really there's only one candidate answer around, and that is to take the corresponding linear combination of the limits. Alpha times the limit of the first one plus beta times the limit of the second one. There's no other obvious, it'd be perverse if the new limit was A multiplied by B. Because look, we haven't done any multiplication of A by B here, we just added them together. So it'd be very strange if it turned out the limit was A, capital A multiplied by capital B. That would be very strange. So, we can prove this unusually sometimes, but we can prove it directly. So I'm just going to produce a big chain of equations. From the top, I have the sum of m equals 1 to infinity of Cm. At the bottom, I'm going to have the actual answer. Now, I could be very brave and say ahead of time how much space I'm going to need. Shall I do it? No. So I'm living on the edge here. So this has to be alpha times capital A plus beta times capital B. Okay, that's what the theorem says the answer is. I have to prove that this is equal to this. Okay. Now, what things am I going to use along the way? Well, I'm going to use two particular things, two main things. Okay, I might use a little bit of algebra manipulation, but apart from that, what properties am I going to use? What facts am I going to use? Well, I'm going to use the definition of convergence for a series. So the definition of what this symbol means, that's the thing I gave at the head of this lecture on your first page of notes. I'm also going to use the assumptions in the theorem, the fact that AM is a convergent series and BM is a convergent series. So those are the tools that I expect to use here in moving from the sum of the infinite series to what its claimed limit is. Okay? So first I use the definition of convergence for a series. And this says that the sum of the series is equal to the limit of the partial sums. So here's a partial sum. And I'll now bring in I'll just leave it a Cm for now. So this is the definition of convergence for series. If this series is convergent, the value it has to be the limit of the partial sums. If you like, you can put some large brackets there just to make it clear. The thing in the brackets is the kth partial sum, isn't it? Adding up the first k terms, C1 plus C2 up to Ck. And outside, we're taking the limit as k goes to infinity. So that is just exactly the definition of convergence for series that I gave you at the start, and that's in the notes. On page 12. I'll just drift leftward slightly. Now I'll just replace the Cm with what it is. This is alpha Am plus beta Bm. Okay, that's just the definition of Cm. Now we do a little bit of algebra. Here you've got a finite sum. Okay, so this finite sum, this infinite sum here is a bit of a strange object you have to handle carefully. It's an infinite series. It only has a value if it's convergent, and the value of it is defined as a certain limit. But this sum here in the brackets now is just a plain old boring finite sum. It's just a finite number of numbers added together, and they're multiplied by these coefficients alpha and beta. So just using, high school algebra, primary school algebra even, maybe, you can re-express this sum as alpha times adding up all the a's plus beta times adding up all the b's. Now, is everyone okay? Okay, so it's a bit more advanced than stuff you do in high school maybe, but really the principles being used are really only high school principles. We're using our sigma notation, of course. In this instruction here says add up all the terms alpha am plus beta bm from m equals 1 up to k. This one says, well, separately add up all the a's and then multiply that sum by alpha, and separately add up all the b's and then multiply that sum by beta, and then add the two sums together. Well, that's just two different ways of adding up the same set of linear combinations. Okay, you're just moving the terms in the sum around, and you're factorizing the alpha out of all the a's and taking the beta out of all the b's. Okay? So it's just algebraic manipulation. I said at the start I was going to use two main tools. However, I see now I have to use a third one. I have to make use of the algebra of limits theorem for sequences. Because if you just stand back a little bit and look at this and say, what are we looking at? What we're looking at is a limit of a linear combination of, and how should we consider these things in the inner brackets? Okay, they look kind of complicated, but really they're just a term of a sequence. They're the kth term of a sequence. This one here is the kth partial sum of the series A. This one is the kth partial sum of the B series. But forgetting that for a moment, really they're just, so you could call this SAK, and you could call this SEK, say. Sorry, so SEK. So this is the kth partial sum of the A series. This is the kth partial sum of the B series. But really, it's just a limit of a linear combination of two sequence elements. So our algebra of limits theorem for sequences applies. So instead of this limit of a linear combination, I can express it as the linear combination of the limits. So you see what I had was a limit of alpha times this k term plus beta times this k term. Instead, I've written it as alpha times the, so I had the limit of alpha times the k term plus beta times the k term. Now I'm writing it as alpha times the limit of the k term, then plus beta times the limit of the other k term. So that justification there is using theorem 1.4, the algebra of limits theorem for sequences, the linearity part. So far I've used the definition of convergence for series, straightforward algebraic manipulation of this linear combination sum. Then I've used theorem 1.4. Well, now I can, see, I gave myself too much room. Now I just move straight to the conclusion. Because this thing here, by definition, this is A. And this second limit by definition is B. Because what is capital A? Capital A is the sum of the A series, which by definition is the limit of the partial sums of the A series. And capital B is in the conditions in the theorem, capital B is the limit of the B series. But by the definition of convergence for series, that is exactly the limit of the partial sums of the B series. Okay? You've got alpha times A plus beta times B. So we have exactly the required thing at the end. And remember, what's on the left of this big equation we're building at the top? It's the sum from n equals 1 to infinity of Cn. And we get it to be the actual value of that limit. Okay? So just finish the sentence as required. This is what we were required to show. Here it is shown. Okay? So that may come in handy from time to time. Anywhere we've got two series that we know converge and we know their limits, or we can at least label them using something, then if we want to form a linear combination of them, of the two series, we can do that. And we can also know that then that new series is convergent and it has the obvious limit. Now, any questions? Anything you'd like me to clarify on that or go over again? So it's a nice kind of proof. It's you when you're reading through these and studying these, understand, you have to appreciate what other results are feeding into it. So mainly we had theorem 1.4 was used, and also the definition of convergence for series. So the definition of what this sum to infinity notation actually means. That was a key to it. Really, it's just proving something about the behavior of the notation, or how to organize the notations. Okay. Third over third, 2/3. Yeah. Let me just give a quick example, as I should. Well, we know already that when you add up all the powers of a half, you get 1. When you add up all the powers of 3, what about this series? Well, applying this result, we can straight away say that sum of this series is minus 2 times the sum of 1 over 2 to the m, plus 5 times the sum from m equals 1 to infinity of 1 over 3 to the m. Now this we already know is 1, this sum, a half plus a quarter plus an eighth and so on. Now when you do it with thirds, let me just check. That's a half, isn't it? So this is plus 5 times 1/2. Now the fact that this is a half is, this will come out of the fact that this is another geometric series. We'll see that shortly, probably tomorrow. So this geometric series here, its sum is equal to 1/2. So then when we form this new series up here, again, it's going to be convergent, and so the whole thing sums to minus a half. Okay? And that's using the results we just proved. Sorry, 5 halves minus 2, which is minus 4. So sorry, it's plus a half. Plus a half. So that's an example of how you might use it. It allows you to say that the sum of this complicated compound series is composed of the linear combination of the sums of the individual series. Okay, now let's move on to the first of our convergence tests. This is the general term test on page 14. Bring that up in the notes. And this refers back to the observations I was making about the two key examples we looked at last time, and which I reminded you of just now. The harmonic series and the series of powers of 2. So we said that these are convergent series. Sorry, the powers of 2 one, part of the reason why it converges is that the step size you're adding on each time is converging to 0. But the second example says, well, okay, here's another series, the harmonic series, its step sizes are converging to 0, however, it still diverges. So what we glean from those examples, what it suggests is that if a series has any chance at all of converging, the step size must be converging to 0. But secondly, that's not enough. There are examples, like the harmonic series, of series whose step size is converging to 0, but still diverge. So how do we record, what kind of firm general results can we drag out of those observations? Well, this is theorem 2.3, which is the general term test. It's got two equivalent presentations there. We'll assume we're dealing with so we're looking at the sum of this A series, A1 plus A2 and so on. So there's two ways to phrase it. Either if we know that the limit of so this limit here on the left, this is the limit of the sequence of terms, AN. If that limit is non-zero, that means your sum is going to diverge. Another way of presenting it is, if you know that your series converges, then it must be the case that the sequence of terms has limit 0. Let's look at the first way. You see, if you've got a sequence with a non-zero limit, that means as n gets larger and larger, the sequence terms are getting closer and closer to this non-zero number. What that means, if you look at the infinite series, as the index gets larger, the series is going to behave like keeping adding on copies of that non-zero limit. So no matter how small the limit is, as long as it's non-zero, if you keep on adding it up, eventually you're going to grow to any size. So you're going to diverge. The series is going to diverge. The other way of looking at it is if you know the series is converging to begin with, so the partial sums are converging towards something, well, that means the partial sums, their changes must be converging to 0, because they're converging to some limiting value. So if you wait around long enough, you'll see the partial sums change very, very little. They'll just be getting closer and closer to their limiting value. And the change in the partial sum is exactly the step. It's exactly the new term in the series you're adding on each time. So that forces you to this conclusion that the limit of the step sizes is 0. So that's a kind of wordy explanation for it. However, we'd prefer just a much more definite, firm, rigorous proof that we can put down. So that's what we'll present now. So this is theorem 2.3, the general term test. And the way we'll prove it is we'll prove that second version of it. So the second of those bulleted points in the statement there. So we'll assume that the A series converges and it's equal to L. So we want to show that the limit as n goes to infinity of just the sequence of terms is equal to 0. And this is let's do a quick proof of this. So notice that the AK, the kth term of the series, is the difference between the kth partial sum and the partial sum that came before it. The AK is the kth term of the series. It's the thing you add on at stage k. Well, here's the partial sum, the kth partial sum. The sum of the first k terms. This is the k minus 1th partial sum, the sum of the first k minus 1 terms. This sum here on the right is almost the same as this sum here on the left. They only differ in one term, and that's that this one has the extra term AK added on. So the AK is the last thing you add on to this sum. And all the other terms in the sum are all contained in this one. So when you subtract them all away, you're just left with AK. And now take limits. So we take the limit as k goes to infinity on the left. And we take limits as k goes to infinity on the right. And in fact, we also apply the previous theorem we've just done. Because really I should take, let's write it like this. I'll just use S for the partial sum now, instead of the sigma notation, just to quicken things up. So we take the limit of both sides. So the limit of AK is equal to the limit of this difference of partial sums. But then by the linearity, I can say this is the limit as k goes to infinity of the kth partial sum minus the limit as k goes to infinity of the k minus 1 partial sum. So there, I've just labeled this partial sum as sk minus 1, and this one here, just label that as sk. Those brackets are pretty, maybe the brackets are in there. Well, see, by definition, by assumption, the series is convergent and it has limit L. So the limit of the sequence of the partial sums is equal to L, because that's the definition of convergence. What does writing this equation mean? That the sum of the infinite series A, M is equal to L. What it means is that the limit as k goes to infinity of its kth partial sum is equal to L. But what's the limit of the k minus 1 partial sum? So we know the limit of sk as k goes to infinity is L. What's happening to sk minus 1 as k goes to infinity? Well, it's converging to L as well. See, sk minus 1 is just the sequence term that is one step behind sk. So it's just one step behind sk. So as k goes to infinity, sk is converging to L, getting closer and closer to L. Well, so is the thing that is just one step behind it. So it's going through the same sequence of terms. If you like, it's just one step behind sk, but in its limits, it's going to be exhibiting the same behavior as sk. Okay. If sk is tending to L as k goes to infinity, so is sk minus 1. Of course, what's L minus L? 0, of course, as required. That's what the theorem asked us to do, to prove that the limit of the sequence of terms AK is 0. So that must happen whenever the series is convergent. So what that means is the way this can work for you is this can allow you to detect not convergence. This is never going to detect convergence, but it may detect divergence. See, when you think about it, it tells you something about how convergent series must look. Convergent series must have terms that converge to zero. But that's not enough to ever help you positively identify a convergent series. But what it does allow me to identify is a series which is not convergent. Okay. Let me just take an example. All of you in this room, okay, let's for argument's sake currently live within the Greater Manchester area. Some of you might not be true. Maybe you're coming in from far away. You've got a lot of okay. But for argument's sake, everybody here lives in Greater Manchester. Let's assume. Okay, that's a feature you all share. But that doesn't allow me to identify one of my maths students. If I go out then and find somebody in the street and say, oh, you live in Greater Manchester, you must be one of my maths students. Because all my maths students live in Greater Manchester. Well, you can tell the logic is wrong there. I can't do that. But what it does allow me to do, if I go out in the street and I meet someone and I say, where do you live? And they say they live in London. Well then I know you are not one of my maths students. Because I know all my maths students live in Greater Manchester. So you see, this example is like this. The proof tells us something about convergent series. It tells us a little bit about convergent series. Their terms must converge to zero. But that will never allow me to positively identify a convergent series, a math student, but it will allow me to, well, one of my math students, but it will allow me to detect someone that isn't my math student. It will allow us to detect a series that isn't convergent. So I know it's 9:50, but just a 1 minute example is this one. Does the sum from n equals 1 to infinity, does this converge? Well, just rewriting the fraction, you see the fraction rewrites to this. 2 to the n minus 1 divided by 2 to the m is 1 minus 2 to the m, which is convergent as a sequence. The sequence of terms is convergent, and what does it converge to? 1. Because it's a constant 1 minus a bit, but the bit is converging to 0. So this converges to 1, and the important thing about 1 is it ain't 0. Convergent series have to have their terms converging to 0. Here's a series whose terms converge to 1. So now we can say, therefore, by theorem 2.3, this series is divergent. It can't be convergent, because if it was convergent, its terms would have to converge to 0. But we've observed that they don't, so therefore it is not convergent. So this is an example of this test detecting divergence. Note that you can't apply this to the harmonic series. This test doesn't tell you anything about the harmonic series. So you look at the harmonic series, you examine the terms, you say, well, yeah, the terms converge to 0. So this test just kind of says, well, yeah, I can't say anything about that. It may be convergent, it may be divergent. That's all this test can say about the harmonic series. Okay, sorry I went a few minutes over there. We'll finish there, and I'll be seeing you again tomorrow. So we'll do maybe another test or two, and then a load more examples tomorrow.